In this final section, we're going to review some AP-style free response problems. All right, so here's problem 1, an AP-style free response problem for heating curves and Hess's law. First, balance this equation showing the incomplete combustion of methanol, CH3OH. So we're going to balance this equation here where CH3OH reacts with oxygen to produce carbon monoxide and liquid water in an incomplete combustion reaction. In part A, calculate the heat of reaction delta H in kilojoules. The heats of formation in kilojoules per mole for each compound are minus 238.08, 0, negative 99, and negative 285.8. Calculate the heat of combustion, delta H combustion, in kilojoules per mole of methanol. C. Calculate the enthalpy change, delta H, when 4.5 grams of methanol is completely burned. D. Is the enthalpy change in part C an exothermic or endothermic? Justify your response. If all the heat calculated in part C were used to heat a 1.0 kilogram sample of water, initially at 22 degrees Celsius, what would be its final temperature? The specific heat of water is 4.18 joules per gram degree Celsius. All right, the first thing we need to do is make sure we're operating with a balanced equation. And right now, a lot of things are actually pretty close to balanced. Carbon is balanced on both sides. There are 4 hydrogens on the left and 2 on the right, and 3 oxygens on the left and 2 on the right. So actually the only thing we need to do is add a water here, and that gives us 3 oxygens on the right and 4 hydrogens on the right, and that balances the equation. You can see here in black the fully written out balanced equation. And then of course, just make sure, double check that the number of elements are the same on both sides. So 1 carbon on both sides, 4 hydrogens, and 3 oxygens. In part A, we're asked to calculate the heat of the reaction delta H in kilojoules. And we're given heats of formation in kilojoules per mole for each compound. So CH3OH is minus 235.08. Oxygen is 0, of course. CO as a gas is minus 99, and water liquid is minus 285.8. So to find the heat of reaction, subtract the standard enthalpies of the reactants from the standard enthalpies, or the heats of formation of the products. So the sum of the heats of formation of the products minus the sum of the heats of formation of the reactants. So the products, I have 2 times the heat of formation for water plus the heat of formation for carbon monoxide. So these are my products minus, I just have 1 reactant, the methanol, and I get minus 436 kilojoules per mole. Part B, calculate the heat of combustion, delta H combustion, in kilojoules per mole of methanol. In the reaction, we have 1 mole of methanol combusted. So the heat of combustion is the same as the heat of the reaction, minus 436 kilojoules per mole. If there were 2 moles of methanol being combusted, so if this balanced chemical equation had a 2 instead of a 1, then the heat of reaction would have been halved, because what we would have calculated the heat of reaction would have been for the combustion of 2 moles, and we're asked for every 1 mole. So we would have just had to divide by 2. But since the reaction is only showing the combustion of 1 mole, it's the same as what we calculated in part A, minus 436 kilojoules for every mole of CH3OH methanol combusted. Part C, calculate the enthalpy change, delta H, when 4.5 grams of methanol is completely burned. So what we need to figure out is how many moles is that? We know how much the delta H is when a full mole is combusted. But what if we only have 4.5 grams? So first, determine the number of moles that represents, and then multiply the heat of combustion by the number of moles of methanol. So the molar mass of methanol is 32.04 grams per mole. Again, just using a periodic table, carbon is 12, hydrogen is 1, and oxygen is 16 approximately. So we have 0.140 moles of methanol. And then if we multiply that by minus 436 kilojoules for every mole combusted, we would get a total of minus 61.04 kilojoules of heat released if we burn 4.5 grams. The other way I like to think about this sometimes, just so I don't forget, we know that 1 mole releases minus 436 kilojoules of heat. So now if we have 0.140 moles, how many kilojoules of heat is that? So it's like a ratio we're setting up here. Or we can just multiply the number of moles by the kilojoules per mole. Part D. Is the enthalpy change in Part C exothermic or endothermic? Justify your response. In Part C, the change in enthalpy was negative. That means that the enthalpy change is exothermic, signifying a release of energy when the methanol is burned. Part E. If all of the heat calculated in Part C were used to heat a 1 kilogram sample of water, initially at 22 degrees Celsius, what would be its final temperature if the specific heat of water is 4.18 joules per gram degree Celsius? So we can use the equation Q equals MC delta T to solve for, we're going to solve for delta T, how much the temperature will rise. And our Q, this comes from our answer in Part C, but we've changed the sign, right? Because now the water isn't releasing the heat. The water is absorbing the heat, which would indicate a positive value for the heat absorbed. So delta T is equal to Q, 61,040 joules. I've converted to joules, and that's to be consistent with my units for specific heat. Over the mass 1,000 grams, same thing here. We know that it's 1 kilogram, but to be consistent with our units in our specific heat, we have to convert to grams and then multiply by C, or the specific heat, 4.18 joules per gram degree Celsius, and we get a change in temperature of 14.6 degrees Celsius. So the final temperature is the initial temperature, 22 degrees Celsius, given in the problem, plus the increase or change in temperature, 14.6 degrees Celsius, and we get a final temperature of 37 degrees Celsius.